Hello, today we are solving a problem for a probable movement, and we will apply the elements of this movement for the next case. Driving a car at a constant speed of 12 meters per second, he drives over the bump of the road, which has a circular cross-section. If the radius of curvature of the bump is 35 meters, find the apparent weight of a person with a mass of 67 kilograms in this car as it passes over the top of the bump. So, we've seen all the data in the problem, and the second question is, at what speed should we drive over this bump to feel weightless? That is, being at the top point, we must experience weightlessness. That is, our weight must be zero. Well, let's start by solving the first problem, where we meet you with the case of a body at this point. And this body is moving at a certain velocity v, which is 12 meters per second. And we should experience a certain change in weight. That is, we should feel a different pressure on the seat of our chair. Why did this happen? Let's find out in terms of the forces that act on this body. Now, first of all, we know that naturally there's going to be a force of gravity on the ground, and the force of support from the surface that we're on. And also, given the fact that we're moving on a circle with a radius of 35 meters, the acceleration will be directed towards the center of that circle. As we remember, the acceleration of the center is rapid. And based on the given forces and the format of motion itself, we can write down Newton's second law, given that we know where all the forces are directed and where the acceleration of a given body is directed. Let's take the axis along which we will work. Y is pointing vertically downwards. It is more convenient because the acceleration is directed vertically downwards. Let's write down Newton's second law in projection on the corresponding axis. It turns out that the travel of the mass on the acceleration of this body will have a positive value because the acceleration coincided with the direction of the y-axis. Further, the force of gravity also coincides with the y-axis and the oppositely directed force of the support reaction. Of all the presented, we are interested in the support reaction force because according to Newton's third law, it is the force that will equal the weight of the body, i.e. the force with which the body acts on the surface itself. Therefore, in order to find the weight of the body, we need to look for the support reaction force in such problems. Now let's express from here the support reaction force. N equals mg minus m for the acceleration. Now our task is to describe the acceleration with which the car is moving at this point. You and I know that the centripetal acceleration will be determined by the formula as the ratio of the square of the velocity to the radius of the arc of the circle on which this body is rotating. We can simplify this expression a little bit and take the mass out of the bracket, and then you get this expression. And actually we know everything for calculation. Let's do the calculation. Mass is 67 kilograms, g is 981, minus the square of the velocity in 12 squared divided by 35 meters. After doing the math, we get a force of approximately 381 and 6 newtons. So the value of the force is less than that. Let's just calculate the approximate value. The weight of a person with a stationary car, that is, for this we will have to multiply 67 by 981, but it will be almost 670 newtons. So we can see that there has been a significant reduction in weight, because really going through such a point is going to show up as a reduction in a person's weight, and we can see that this value has become much smaller. So now the second question. We need to calculate the velocity to which the car must move in order for a person to be in the upper point of this bump in weightlessness. So it turns out that for the second, the weight of the person has to go to 0, which means that the force of the support reaction at that point must also be 0. For this purpose, what should we do? We equate the expressions we get to 0 because the support reaction will still be described by this formula. But we can now equate this expression to 0. Then it turns out that mass times the difference between g and v squared divided by r will equal 0. Well, and from here it turns out that, of course, m cannot be equal to 0, then this expression will be equal to 0. That is g minus v squared divided by r equals 0. From here it is easy to find the velocity of the given motion. In this case we've labeled this velocity as v1. So let's replace it, and we get from here a ready expression. v1 is the root of g times r. Accordingly, supplying the value in this formula, we get a velocity of about 18.5 the meters per second. That is to say, the velocity must of course be greater, because we see that at 12 meters per second the weight is there, even though it's less, but at 18. 0.5 meters per second, the weight can disappear completely, and the human body can be in weightlessness for a moment. These are the tasks we have considered with you today. See you in our next lessons. Goodbye.